Here is a short list that you're going to need to understand before we get to that complex picture I was talking about of conductivities of various materials. Not listed is bakelite, which is what we're going to be looking at, which is a plastic used for more than a century now. It was first marketed in 1907. I think it was the first plastic that, the first polymer that used formaldehyde as the solvent. But it has a slightly lower conductivity. That is, bakelite has a lower conductivity than the Teflon shown here. Teflon is a polytetrafluoroethylene. Bakelite is a thermal resistor, and its conductivity is 0.21. Very low conductivity. Look here also, you'll see copper, which is inside the box you're going to look at. Copper has a conductivity of 401 watts per meter. So that's a very high conductivity, as does gold or silver, even higher at 429. So they're good conductors. Wood is, of course, a very poor conductor at the bottom of the list at 0.13. So you need to know a little bit about conductivity of materials that you're looking at. Emissivity is a dimensionless number. It's a ratio, but we express it as a decimal, so it becomes dimensionless. It is the coefficient expressed as a decimal of the amount of energy that conducts to the surface of a mass and that emits or radiates from its surface. You need to understand this. This is a very brief listing of some of the various emissivities of a few things you'll run into. Notice here the polished copper, and then what happens to it when it is heated and it oxidizes. A very critical issue to a thermographer, an issue that you're going to deal with when you're actually writing a report. Why do you need to cool off this copper conductor, contactor? Because it's going to oxidize, and when it oxidizes, it's going to lose more of its heat, but it's also going to generate more of heat. You become a high resistant joint. Okay, so the emissivity changes over temperature range and with oxidation, but the number rises in the copper from about 5% or 0.05 to 0.78 or 78% of the emissivity. Many conductor devices you will see are made of these metals, and herein lies the issue. When the temperature rises again, they oxidize. They emit more of their energy, but this indicates the heat is building in the device and it's moving towards criticality. It'll catch fire, the insulation could catch fire, or it could actually explode if it got hot enough. In the complicated device that we're going to see next, you need to understand this also. Now we're to the complex issue we were discussing. This is a breaker box. It's a complex picture. Why? Because you have a lot going on here. So what is the hottest point is the question. Where is the actual problem? Well, it turns out to be the internal contacts are the hottest point, but the hottest apparent point is the external contact. You could actually see at the lower left if this were a visible light image, if it were what we call a real-time image. Okay, but think about how the heat comes to your imaging device to make the image that you're looking at. Okay, it's apparent heat, right? So how did it get there, and how is that complicated? In this case, it is made by high resistance internal contacts inside the device and wicking out to the contact that you see at the outside of the device to the left. But from there it radiates. But from there on the internal contact, that is, both of them are radiating to your device. One is radiating directly through the external contact that you can see, but the other one radiates where the contacts are, the hottest point, radiates into the void that's around it. There's a little bit of air in there, right? The air convects, becomes hot, eventually becomes stable, and that further oxidizes those contacts, making even more of a problem. But some of that convects into the bakelite that is the box itself. It's a black or gray or brown box, and then poorly through that bakelite. Remember, the conductivity was very low. It was 0.21 through that bakelite and out to the imaging device. So as a thermographer, you're seeing only a fraction of the heat that is actually inside the box. Remember, the zeroth law saves us here as thermographers, but destroys the contact slowly, because the hot contacts seek to equalize within the small air void to both the bakelite on the outside, but it's draining out through there. It's seeking to equalize it also to the contacts, which are actually giving off the heat, but some of that heat goes back to that contact. It's convecting, right? So the heat is in both directions. The air void with the contacts and the bakelite, it's trying to seek that equilibrium. So that's the zeroth law. And eventually all the heat dissipates, but more electric energy is coming in, the resistance gets higher, the heat increases, so you have a heat flow out to the thermal imaging device every second that this device is on. Only when it's off does it reduce down to ambient temperature, right? So this apparent 26-degree rise that you can see on the right side of that image but it's on the thermal contacts will become a 50-degree rise in a year, and then become critical about 6 months after that, somewhere in that range, according to how it's used. However, the internal contact is already probably 100 degrees C above the ambient. It's critical right now. It could fail now. It could blow up or start a fire. Most likely it'll keep tripping this device, and they won't know why the device is tripping. Well, the device is failing, and that's better than causing your system to fail in some other way. That's what the breaker is there for. This breaker box needs to be replaced, and it needs to be replaced now. In this case, it's tripping constantly. That's better than the other alternatives. But this is how understanding the law of thermodynamics, the laws of thermodynamics, helps you as a thermographer. Without them, you understand what the apparent temperature tells you through the image, but that could be what would be classed as serious now is classed as an immediate problem that needs to be fixed. It's a critical problem in reality. So that's the ISO standard. So let's take a look at those to understand that. The text that you see here is actually an image, even to me, put into the PowerPoint. It was actually copied directly out of ISO standard 18434-1, the International Standard for Thermal Imaging Problem Categorization. It is easy to work with, where the lowest priority is every problem below 10 degrees centigrade, and is classed as an advisory. In other words, tell the client about the issue. You've got an issue here, just be aware of it, or track it, put it in your preventative maintenance program, or next time you are doing maintenance, tighten this up, whatever your advice to them might be. But from 10 up to 20 Celsius, or twice the temperature rise, the issue is classed as intermediate. This is becoming more of a problem. And remember, this is going to, the time will be reduced moving from one to another, even though it doubles, and then it doubles again. So from 20 to 40, again, double the previous rise, this issue would be classed as a serious issue to be dealt with. Above 40 degrees centigrade, rise from the ambient temperature, that is, it's classed as a critical problem. So the problem pictured here, again, what first looks like a 26-degree rise is a serious problem. It's really a critical problem according to this standard. Serious can be a common term, it can be ambiguous a bit, but critical. This is a critical issue that needs to be dealt with quickly. Well, as we have seen, thermodynamics relates to virtually everything. As we saw in the first module, there are fundamental laws of science. They are fundamental laws of science, and all other scientific laws are derived from them in one way or another. They are applicable to all machines and animals, from medical issues to machinery, mechanical issues to electrical issues, from equipment failures to fires and explosion. It's all about the energy in the system and how efficiently that system is operating at the energy level that it's required to operate at, or that it does operate at. And thermodynamics can give us a lot of information about those systems and how they operate and how they are operating.